Good morning, students. In today's GATE class, we are going to discuss about analog circuits. Before moving to the problems discussion, that is previous year GATE problem discussion, we'll discuss now a basic concepts about a clipper, clamper, and rectifier in analog circuit. Today topic is clipper, clamper, and rectifier. Before discussing about the GATE questions, we'll discuss or recall some basic concepts of clipper, clamper, and rectifier. So now clipper, you know the basic concept, but anyway we recall it now. So clipper is otherwise called as a limiter or a slicer. So why it is called as a slicer or limiter means we are going to removing some peak value of a waveform, that is input signal. The input signal may be any kind of signal, analog signal, that is sinusoidal signal or square waveform or rectangle waveform. It may be any type of signal. So in that input signal, peak to peak value, in the peak value, some portion of peak value we are going to remove. That is limiting. We are going to slice it off. So see in the diagram. So blue color is waveform, input waveform. In that blue color input waveform. So this is your output. V out is in the red color. So here the peak value is sliced off in both positive and negative. If we are doing this in a positive cycle means it is called as positive clipper, and the clipping of removing in a negative peak value means that is called as negative clipper. Okay, so these are the classification of clipper, positive clipper and negative clipper. Positive clipper, in positive clipper. Okay, before that, so why we are using this clipper? In which application we are going, which in what condition we are going to use this clipper means if for an over voltage or a low voltage condition, for protecting a circuit against over voltage and low voltages, we can use this clipper concept. So the first category, first type is a positive clipper circuit. So in the circuit diagram, the main parameter, the main component is a diode. So you know the basic concept of the operations of a diode. A diode will be having a two terminal, that is an anode part and a cathode part. So when diode will be in an on condition, that is forward bias. When the diode will be in a reverse bias off condition means a diode will be in a forward bias, that is a short circuit. When anode part will be having a higher value, that is a positive value, and cathode will be having negative value. So in that condition, a diode will be in a forward bias. So now the diode is used here, parallel connection with the load resistor RL. So this is your input signal. I am going to give an input signal as a sinusoidal signal. For example, the sinusoidal signal or value is ranges from 0 to 10 voltage. That is positive 10 voltage to negative 10 voltage. So from 0 to 10, that is 0, 1, 2, 3 up to 10. Again a reverse value of 9, 8, 7 up to 0 value. So the positive half cycle is moving on through a resistor. So what happened to a diode? The diode is connected, anode is connected here and cathode is connected with the ground. So anode part is having a positive value. The positive value means anode with the higher value than a negative part, that is a cathode. So obviously the diode will be in a forward bias. So on condition. So the on condition of a diode, what happens? It will be in a short circuit. So once it is short circuit, all positive value of voltage is moving to a ground. So through across the load resistor R, what is your voltage drop? Nothing, 0. So during positive half cycle, diode will be in a forward bias, so no voltage at the output. A basic breakdown, that is basic breakdown voltage we are getting, that is a 0.7. Okay, so during negative half cycle, so negative half cycle, what happens to a resistor R1? The negative value will be getting at the anode part, so the diode will be in a reverse bias off condition. So what is your input? The input, whatever the input you are giving, you are getting at the output side, collecting at the output side. So the full reverse bias, that is full negative half cycle will be collecting at the output. So what happens? The circuit will be, the waveform will having only negative half cycle. There is no positive half cycle. So this is called as positive clipper. Clipper means slicing off. So the full input half cycle is clipped off. Okay, limited. So that is called as positive clipper. So moving to a negative clipper concept, the reverse concept of positive clipper. Only one just a diode connection is changed. Okay, so another end of R1, the cathode part is connected, anode is connected to the ground. During positive off cycle, what happens? Diode will be in a reverse bias, that is an off condition. So what happens if it is an off condition? It is an open part. Open part means all the value of input will be collected through a output resistor RF. So during positive half cycle, you are getting full without any disturbances. Full output you are getting at the output side. Okay. During negative half cycle, what happens? Reverse concept. That is, reverse means it is forward bias means in negative half cycle it will be a forward bias. Forward bias means short circuit. Short circuit means it only go through a ground. So there will be no output at the output side. Okay. Basic negative value of breakdown voltage you will get, that is minus 0.7 voltage. So this is the concept of positive and negative value. So this is a both combined waveform of positive clipper and negative clipper concept. Why we are getting that breakdown voltage means the practically breakdown voltages for germanium is 0.3 and 0.7 for a silicon. So we are using silicon type of diode. So we are getting plus 0.7 for positive clipper and minus 0.7 for a negative clipper. So next is the clipper concept, positive clipper concept with the biasing. Biasing means externally we are giving some external voltage. For example, 10 voltage input means here the biasing voltage we are giving as a 2. So let's discuss the operation. During positive off cycle, again the same concept, it will be in a forward bias. So in forward bias means it will be a, what happens, it will be in a short circuit. Short circuit means through a resistor R, we are getting only a biased voltage. Here the biased voltage, for say for example, biased voltage is giving us a 2 voltage mean from 0 to 2 voltage we are getting output. After 2 voltage, what happen? After 2 voltage, it will be in a negative. That is reverse bias, open circuit. Open circuit means we are not getting any value. We are not getting any output through a resistor RL. So it is clipped off. So on the reverse concept, negative full negative half cycle, we are getting at the output. So this is called as biased positive clipper. So biased negative clipper means the same concept, only the connection is different. See here, the diode will be positive, that is anode, and cathode is connected through a positive value of biasing. Here the reverse. Anode part is connected to the negative value of biasing. Again, here the biasing external voltage is negative value I am going to give. So negative value if you are supplying here through an anode part means what happens? Full positive cycle we are getting at the output side, and negative half cycle up to minus 2 value. For example, minus 2 external voltage we are giving means up to minus 2 voltage you are getting an output. After minus 2 voltage, that is minus 1 peak value of minus 2, here it is clipped off. So this is called as biased negative clipper. So next is the combinational circuit. If both the positive and negative clippers are combined in one circuit, that is this combination. Diode D1 and D2 both are connected. So what happens simultaneously from this value to this value? Here the example of 5 voltage is given. Okay, 5 voltage means already breakdown voltage is 0.7. So 5 plus 5.7. So 5.7 up to 5.7, from 0 to 10 left up to 0 to 5.7, the value will be getting at the output side. Okay, we are getting output from 0 to 0.7. After above 0.7, what happened? Sorry, 5.7, what happened? The diode will be in a reverse bias, so it will be flipped off, flipping off. So no output after plus 5.7 voltage. The same concept, reverse. In reverse category, up to minus 5.7, we are getting output. Above minus 5.7, negative value of flipping is happening. Okay. So next is the application. So where we are using this clipper practically. So this clippers we can use in a television receiver part. So for synchronizing of input signal with the output signal, that time we can use this clipper as an application. So see here, this series clipper and this are employed in a noise limiting in an FM transmitter. In FM transmission and reception part, definitely we are facing some noise problem. So that noise problem can be eliminated or limited by using this clipper concept. Okay, next is a clamper. So in a clamper, what is meant by a clamper means shifting. What is meant by clipper? The next concept is a clamper. So clipper is a removing part. So what is meant by clamper? Clamper is shifting of your input signal. Shifting means, say for example, this input voltage is from peak to peak value 10 to minus 10 voltage means the whole value, that is whole part of input signal is totally shifted, either positive or negative. If it is shifting to positive, that is above x-axis, above this point means it is called as positive clamper. Positive portion, it is moving off, that is shifting. So that is called as a clamper. If it is shifting to a negative part means that is negative clamper. So here we are using a diode. Diode is connected with a capacitor. Okay. So this is why we are using this clamper means for increasing the value of input voltage, that is wavelength of the input signal, and also it is used in a sound system amplification. Okay. So the next is a positive clamper. Again, clamper is categorized into two types, that is positive clamper. Again, next one is a negative clamper. In a positive clamper, here the same diode is connected with a capacitor. Now what happens to the capacitor? Now it is connected with this input signal. Here is negative half cycle and positive half cycle. So the capacitor starts to charge up to negative peak value. After charging, definitely it's going to discharge. So that is the concept here. During negative half cycle, what happens? Diode will be in a forward bias. So forward bias means it allows the capacitors to charge up to negative peak value. Negative peak value means, for example, minus 10 voltages means up to minus 10 voltage is going to charge. After that, minus 10, 9, minus 9. So again it's going to discharge. So during negative half cycle, a diode will be in a reverse bias. The capacitor can only discharge through a resistor RL. After charging, obviously it's going to discharge. So what happened to your output waveform? It totally is going to shift from the zero value, 0 point. So totally shifted to a positive part. So it's totally shifting. So shifting is called as clamper, right? So the total value of voltage is totally shifted to a which part? Positive part. So that is the concept of clamper. So next is the negative clamper. Only the diode connection is reversed. Here it is connected. The capacitor positive part is connected with the anode and negative part is connected with the ground. Okay, next is the negative clamper. In negative clamper, the diode connection is reversed. So here in the positive half cycle, so during this positive half cycle, what happened to your negative half cycle? Here forward bias. Here just opposite, a reverse bias. Negative half cycle is a forward bias. So the value of input signal is totally shifted to a negative value. The clamper is shifting, right? So negative value, negative part it is shifting, so it is called as negative clamper. Next is the rectifier. You know the rectifier is conversion of just you are moving, that is converting an AC signal to a DC signal. That is the concept of a rectifier. So the rectifier we have two categories, that is half wave rectifier and full wave rectifier. How we are going to implement this using a circuit diagram means we are going to use a transformer. For a half wave rectifier, that is you are converting an analog sinusoidal signal to a DC signal. That is AC, current is converted to a DC. So that is AC, that is this is your sinusoidal AC signal is converted to a DC. During positive half cycle, what happened? You are using only one diode in a circuit. During positive half cycle, what happened? Diode will be in a forward bias. So positive half cycle alone you are getting. Okay, next you are moving a negative half cycle through this transformer. So secondary transformer will be having, it will give a negative half cycle. So during negative half cycle, the negative value is removed. Why it is removed? Not getting output means the diode will be in a reverse bias. Reverse bias means open circuit. We are not getting any output at the load resistor. So it is off. So the value of output is 0, nil. So we are getting DC signal. So this is an AC signal and this is a DC signal. Okay. Next is, so this is the output frequency value for this. When input is F in, the output is F out. So when input is F in, the output is F out. For next is the full wave rectifier. What is this full wave rectifier? Again the same circuit diagram. Instead of using a single diode, we are using a two diode concept. So two diode we are using here, D1 and D2. During positive half cycle, what happened? Diode D1 will be on. During negative half cycle, diode D2 will be in on condition. So parallelly we are getting positive half cycle in the first half cycle, negative half cycle also we are getting again a positive cycle. So what happened now? We are getting double the value of the input signal, that is the value of output. But what happened to your half wave rectifier, F out is equal to only F in. Here two diodes are used, so we are using an output is equal to double the time of twice the time of input signal F in. Okay. So the next is center tap. The same full wave rectifier we are using with the concept of center tapped transformer. Instead of using a normal step up transformer, we are using center tapped step up transformer. So, what is the main drawback in center tapped step up transformer means the implementation. The main drawback is implementing that the circuit will be a bulky one. So cost wise, obviously a high cost. So implementation is also very difficult. That's why they are using practically in many places normal type of transformer. So in center tap transformer, what happens? The same concept during diode D1 and D2. Positive half cycle this diode D1 will be on and negative half cycle D2 will be on. So this is the value of DC signal. So analog circuit AC signal supply you are giving at the input side and getting DC signal. The next one is a full wave bridge rectifier. In a bridge rectifier, this is a bridge connection. Bridge connection means parallelly, simultaneously, we are going to use the four diodes D1, D2, D3, and D4. Okay. So during positive half cycle, what happened? D1 and D3 will be in on condition, and negative half cycle D2 and D4 will be in on condition. So this analog signal is converted to a DC signal. AC signal is converted to DC signal. So these are all the advantages. Center tap is eliminated because the implementation is high, quite complicated, and cost-wise it is high. Okay, next. So far we discussed the basic one. We called all the basic concept of clipper, clamper, and rectifiers. Now we'll discuss about a gate question. So this is your first question. For the same AC voltage and load impedance, which of the following statement about rectifier or current? Okay, so the first statement is this one. Just you read it. The average load current in a full wave rectifier is twice that in a half wave rectifier. Average load current in a full wave rectifier is n times that in a half wave rectifier. Next is a half wave rectifier will be a bigger size transformer compared to a full wave rectifier. Half wave rectifier will have a smaller, that is small size transformer compared to a full wave rectifier. So which one will be a correct option? Yes, it is A and B. Because average load current in a full wave current compared to a half wave, we get twice the value, right? So the first option is correct. So A is correct. Next, what happened? Average current in a full wave n times, not n times, only the twice the value. Okay, not n times. So this option is wrong. Moving to the C1, half wave rectifier will have bigger size transformer than a full wave. Not at all possible because we are using a full wave rectifier, two diodes. Here we are using only one diode. So it is a smaller size of transformer compared with this. Okay, in the transformer also smaller size. So the option A and B both are correct statement and B and C are a wrong statement. So the answer is A and B. Okay, so moving on to the second question. A off-wave rectifier uses a diode with a forward resistor RF. The voltage is Vm, that is input signal is given as a Vm sin omega t, and the load resistance is RL. The DC current is given by. So you solve this question. I'll give time. Just 1 minute time I'll give you. Make it fast. You can solve this problem. A half-wave rectifier uses a diode with a forward resistance. Okay. You have a forward resistance of resistance value RF and load resistance RN. What is your DC current? So input voltage is given as Vm sin omega t. Okay. This is a half-wave rectifier. In a half-wave rectifier, you know, diode is only one diode. So input signal is Vm sin omega t. Only one diode you are using and load resistance RL. So now we are replacing your diode as a what? Forward resistance RL. Okay. So what is your equation for this half wave rectifier average current or a DC current? Im by pi, right? So in Im by pi, what happened? What is your value of current here? The circuit, what is your value of current? Series combination of RF and RL is connected. Input is Vm sin omega t. Then what happened to your current value I? I is equal to what? Ohm's law, V by R, right? No. So Vm sin omega of t divided by RF plus RL. So what happened to your Vm divided by R? We can replace it as Im sin omega of t. So Im is equal to what happened? Vm divided by Rf plus RL. So your Im value here is I is equal to V by R. Both are connected in a series combination. So resistors both are added. So now itself you can able to answer. What is the value of this? What is your correct answer? resistor RF and RL is given. So both the resistors are connected in series. Definitely will getting both the resistors. So option B is correct. Okay. So IM value is what? VM divided by RF plus RL. So what happened to your IM? IM value is substituted in an average value. Average value formula is IM divided by pi, right? So your answer is VM divided by pi RF plus RL. So the option B is correct. Okay. Moving to the third question. For a full wave rectifier, okay, this is the question under which category? Full wave rectifier concept. 4-diode bridge rectifier is claimed to having the following advantages. So you should know the advantages and disadvantages of bridge rectifier and full wave bridge rectifier with a normal transformer rectifier. Okay. So first one is given as less expensive transformers, smaller size transformers, suitable for high voltage application. Which one is correct? Which one is correct? Yes, all the three options are correct. Less expensive. Full wave rectifier, 4 diodes. Okay, less expensive. In a bridge rectifier, we are having a normal. In bridge rectifier, we are using normal step-up transformer, step-down transformer. But in a full wave rectifier of shunt attack, what happened? It is bulky and costly. Why it is costly? Why its implementation is costly? That is quite difficult. Means we are tapping concept and all at center. Tapping at center is very difficult when compared with the normal transformer. So cost wise and implementation wise and circuit or the size wise, so everything are complicated. So less expensive transformer is correct. Okay. So what's the next? A and D are correct because only 1 and 2 are correct. 1 and 2 are correct, and also it is suitable for high voltage application. Okay, so it is used for high voltage. Okay, in bridge rectifier, it's not suitable for a small voltage application. Only using for high voltage application. Why? Because means the output voltage at the time in a bridge rectifier, 2 diodes will be on condition. So in bridge rectifier concept, your output will be V0 is equal to Vm minus 2 voltage of a diode. But in the case of 2 diode concept, that is in the case of half wave rectifier, V0 is equal, that is output voltage is equal to Vm minus V diode. So only one diode. Here it is Vd, but in a bridge rectifier it is 2 Vd. Okay, so 2 Vd means it is not suitable for small voltage application, only it is suitable for high voltage application. So the option, okay, so 1, 3, 2. All the three statements are correct. So A and D is the correct option. Okay. Then moving on to the next one. Design a circuit using 2 idle diodes, 1 resistor and 2 voltage source that would convert the input voltage to the output voltage as shown that the resistor values need not to be specified. Okay, so this is the value of, sorry, this is the input waveform is given. So for this corresponding input waveform, this is your output waveform. So for this, you should draw a suitable circuit diagram. So what is your suitable circuit diagram? So see this output waveform. In a positive half cycle, your peak value is clipped off. In negative half cycle, also peak value is clipped off. From this, definitely we can understand that this waveform is a clipper. What clipper? Both positive and negative clipper. Both positive and negative means what happened? What type of circuit it is? It is a combinational circuit. Combinational circuit means what happened? So two diodes are connected in a parallel combination. At where it is clipping up to 5 voltage. Up to 5 voltage we are getting output above 5 voltage. In both positive peak and negative peak, it's clipped off. That means 5 voltage of biasing we are giving. Okay, so from this diagram itself you can able to understand. You should know what type of waveform it is, what type of circuit you should draw. Okay, so this is the suitable diagram is combinational clipper. Combinational clipper concept only will have positive clipping and negative clipping simultaneously. Okay. Next, we are moving on to the next question. The circuit shown in the figure. So this is your circuit given here. What type of circuit it is? Option A is a bridge rectifier, ring modulator, frequency discriminator, and voltage doubler. Across the diode, anode part, this is your diode D1 and diode D2 part. So it is the cathode part, anode part. Anode part we are taking an output and cathode part we are taking an output. So what happened to your output here? The output is doubled. Okay, so definitely it is not a bridge rectifier. There is no bridge connection. Bridge connection means definitely you will have four diodes. So four diodes. Here in the diagram, there is no four diode. What is a ring modulator? Again, it's not a type of a modulation type of waveform. That's circuit diagram. So next is a frequency discrimination also not possible. Only you are getting a double the value of voltage you are getting at the output. So obviously it is option D, voltage doubler. Okay. Next. Next we are moving on to a next question. In the full wave rectifier using two ideal diodes, VDC and VM, or VDC and peak value of the voltage respectively across a resistive load. If PIV values, okay, peak inverse value, PIV means peak inverse voltage, okay, peak inverse voltage of the diode, then the appropriate relationship for this rectifiers are, okay. So what type of rectifier is full wave rectifier? For a full wave rectifier, if your PIV value is reverse, means what is the value of VDC? You solve this question. You solve this question fast. It's a full wave rectifier. So from the option you can able to answer. From the option, see the option. No need to derive this one. See the option. This is a full wave rectifier. Full wave compared with your half wave rectifier, all the values are doubled in full wave rectifier, because in half wave you are using one diode and in full wave rectifier you are using two diodes. So what happened? Definitely a VDC value is twice the value of twice the output of half wave. So it is 2 Vm divided by pi. Then what happened to your PIV value, peak inverse voltage? Peak inverse value voltage is also twice the value of half wave. So option B is correct. From the option, see here, no 2, here only 2. Okay, here it is 2, here it's only Vm, there is no 2. What is the value? Here both we are having a single value, there is no 2. Obviously from the option you can, no need to derive this derivation answer. Okay, from the option you can answer. So the next question is this. See the diagram, see the circuit diagram. The input waveform is from positive peak plus 50 to minus 50. That is given at the input side. So this is your biasing. What type of circuit? First identify what type of circuit it is. What type of circuit it is? Positive clipper. Positive clipper with biasing concept. So this is a diagram of positive clipper with biasing. Here the biasing voltage is given as a 10 voltage. Okay, so from the option, all are given as a positive clipper. That you can able to understand from the diagram itself, and also in the option also they given positive clipper. With what peak value is clipping off? So that is a thing. So just solve it. So negative peak. What is the negative peak? In a positive clipper, full positive half cycle is clipped off. Okay, up to what value? Up to 10 value it will exist. Remain to a negative peak value. You see positive peak. That means it is stop up to 10 voltage, right? Here it is given 50 voltage. Here it is given 60 voltage. Okay, you just choose the answer from the option just by neglecting remaining options. First one is won't come because it is 50 voltage, because here it is given as a 10 voltage as a biasing voltage. Here it is 60 voltage. Definitely this option also won't come. Okay, then moving to this and this negative peak, up to what value they are giving? Minus 50. But here in the option you are having minus 50 and minus 10. Okay, this also deleted. Okay, these three options won't come. Only we are getting minus 50 voltage negative peak. Okay, if you are clear in your diode concept, that is a clipping concept, clamper concept, these questions are very simple. Okay. So the next question is, two silicon diodes with the forward voltage drop of 0.7 voltage are used in the circuit. The range of input voltage VI for which the output voltage V naught is equal to, the condition is given here. See the condition. See the condition. The range of input V naught is equal to Vi is given. So in this condition, what is your value of Vi. So what is your value of input voltage exists from where to where? Okay, so solve this problem. To try to solve this problem. To try what type of circuit it is first. It is combinational circuit. Combinational circuit means two diodes are used, connected in a parallel, and supply is given as a negative value of supply -1 voltage and positive value of supply 2 voltage. Just you apply the concept. Apply the concept. Working condition of diode D1 and D2. In which condition it will be in forward bias and reverse bias. Just apply it and calculate the answer. Okay. So during this D2, the diode D2 during positive off cycle, what happened? What happened during positive off cycle? Diode D2 will be in a, see here, diode D2. D2 will be in a forward bias. When diode D2 is in a forward bias, what happened to your voltage, input voltage? So this is not V out, this is VI. Okay. So what happened to your input voltage VI? VI voltage will be definitely here it is given as a 2 voltage. No, always the VI will be greater than 2. It's not only 2, we are having a basic breakdown voltage of a diode 0.7. Okay, silicon type of diode we are using, so we are getting a breakdown voltage as a 0.7. So 0.7 plus 2, what happened? 2.7 voltage. So VI is greater than 2.57 voltage. So during reverse bias of the diode D2, what happened? Vi is less than 2.7. Okay. When a diode D2 is in a reverse bias, what happened? Vi voltage is greater than -1.7 voltage. And D1 will be in a forward bias. At that condition, what happened to your input voltage? Vi is less than -1. Here, see, it is -1. Already D1 diode basic or breakdown voltage is -0.7. What happened? -1 -0.7 will become 1.7. Okay, these are all the 4 conditions. You analyze this 4 conditions. So the condition is given here, the range of input voltage Vi for which the output voltage V0 is equal to Vi. Which condition V0 is equal to Vi? When the diode D1 and D2 will be in a reverse bias. If both diode D1 and D2 is in a reverse bias. Reverse bias means what happened? Both are open circuit. Open circuit means what happened? All the value of Vi will be collected over here. Okay, so when this Vi is equal to V in, what is your condition? At this situation, this V in is equal to V naught means both the diode should be in a reverse bias, that is open circuit. So at that condition, what we are getting when diode D1 is in a reverse bias, what is your input voltage? Input voltage is greater than -1.7 voltage. And when your diode D2 is in a reverse bias, what happens to your input voltage Vi? Is less than 2.7. How we are getting 2.7? This is your 2 plus 0.7, 2.7, and this is your -0.7 and this is -1. So -1 -0.7 will become -1.7. So which option is correct one? So D option is correct. So Vi will be ranges from -1.7 voltage to 2.7 voltage. Okay, at which condition? The condition is important. V0 is equal to VA. V0 is equal to VA means what is indirectly mentioning here? Diode D1 is D2 are in what? Open circuit. Open circuit means reverse bias. Okay. So the next question is this one. Okay. If the circuit shown has the function as a clamping circuit, then which one of the following conditions should be satisfied for the sinusoidal signal of period T? Okay. So this is your concept of clipper or clamper. Clamper circuit. So this is a diagram of a clamper. For a clamper circuit, which condition is possible? Check out your answers. Which one is possible? The explanation is given here. The circuit is of negative clamper. I told you, no, by seeing the circuit itself, you can able to judge this is a diode and this is a capacitor is connected, means it's a clamper. It's a negative clamper. Okay. It's a negative clamper. When diode is in off, the capacitor, what happens? Discharges through a resistor R. The output falls exponentially with the time constant RC to avoid the discharging of the capacitor. So RC time constant, that is R and C value will be greater. Okay, the T is the time period of your sinusoidal signal applied in your circuit at the input side. So the time period of sinusoidal signal t is given here. It will be what happens? It's lesser. T time period is lesser than your R and C value. So this is your R value and C value. So this option is one correct one. D option is correct. Okay. Moving to the next one. See, solve this problem fast. In a positive clamper, the diode connects when? It's clearly given. It is a type of clipper. Clipper in which type? Positive type, positive clipping. Diode conducts when? At which condition? At what condition the diode will be in an on? That is forward bias. At what condition it will be on? When your reference voltage is equal to your input voltage. The reference voltage may be any voltage. Say for example, input voltage is 10 voltage, the reference voltage can be a 2 voltage or 3 voltage. Okay, so that at that point of 2 voltage, the positive half part is clipping. So it is equal. Okay, it should be equal. So that is your option B. So next, moving on to the next question. Read the question. The positive small signal half wave rectifier. So half wave rectifier question is given. Half wave rectifier, rectify the signal with peak value only. Okay, rectify the signal with value of few millivolts only. Rectify the signal with both peak value and down to few millivolts. Okay. Next is none of the mentioned. What happened to your positive small signal half wave rectifier? Rectification is nothing but conversion of AC to a DC. What happens? It's only from the option you can able to answer. What is your answer? Rectifies a signal with a value of few millivolts one. Okay, sorry sir. Rectify the signal with both positive peak value and down to few millivolts. Okay. So next question is 1 minute. Next question is how to minimize the response time and increase the operating frequency range of the op-amp. Okay. Positive half wave rectifier with 2 diodes, positive half wave rectifier with 1 diode, negative half wave rectifier with 2 diodes, negative half wave rectifier with 1 diode. So which one is the correct option? Half wave rectifiers with how many diodes? How to minimize the response time and increase the operational frequency range. So which one? The option is C. Negative half wave rectifiers with 2 diodes. Why negative half wave rectifiers? We have the 2 diodes and use so that the output of the op-amp does not saturate. Okay. So the next question is the applied input AC power to a half wave rectifier is 100 watts. The DC output power obtained is 40 watts. So the question asks this. So this is your input data. Input data is a given value 100 watts. Okay. So question asks this. What is the rectification efficiency and what happened to the remaining 60 watts? So first you should calculate what is your efficiency of the rectification efficiency. So what is your efficiency formula in the rectifier? You know it is efficiency means what? Output divided by input. No, what is your output of the rectifier? Input is AC signal and output is DC signal. So output divided by input means DC output power divided by AC output power. This is your formula. No, simply you just substitute. DC power is what happened. AC is given as 100 and DC output is 40. So 40 divided by 100, 0.4, it is 40%. Okay, these questions will be coming under in a GATE question paper. That is part B. That is part B in 2 marks questions. Okay. So the next one is, what is the second part? What happened to a remaining 60 watt? What happened to your remaining 60 part? How much power efficiency you are getting? Okay. So how much? So this is your 40. You are getting 40% of the rectification efficiency. See this question, 40% efficiency of the rectification does not mean that 60% of the power in the loss in the rectifier circuit. In fact, the crystal diode consumes little power due to its small internal resistance. The 100-watt AC power is contained as 50 watt in a positive half cycles and 50 watt in a negative half cycle. The 50 watt and the negative half cycles are not supplied at all. Only 50 watt in the positive half cycles are converted. Okay. So what is your power efficiency? What happens? Again, power efficiency for calculating the power at the output side. Okay, power at the output side divided by power at the input side. So that is your 40 and that is your 50 value. So when dividing into 100, into percentage you are calculating, so into 100, so 80%. Moving on to the next question. So for this type of questions, you should know the formulas, basic formulas of rectifiers. Okay, without knowing this formula, it is not possible to solve these questions. So you should memorize, you should understand what is the formula for corresponding topic. A half-wave rectifier is used to supply 50 volt DC to the resistive load of 800 ohms. The diode has a resistance of 25 ohms. Calculate AC voltage required. What is your AC voltage required? Simple, it's very simple. No need to analyze anything, just a simple formula. So first you should know what are the given data. So first write the given data. So VDC, that is the voltage of DC value is 50 voltage and diode resistance value is 25 ohms and load resistance RL is 800 ohms. Okay. So what they are asking, what is your question? As the diode has a this one 25 ohms means what happened? Calculate AC voltage required. So AC voltage required is what? Okay. So for calculation, what is your value of VDC? DC value is equal to voltage Ohm's law, V is equal to IR, IDC into RL. What is your IDC? The first question itself we discussed what is IDC. IDC I told you no, IM by pi. Why IM by pi? This is half wave rectifier. For full wave rectifier means what is your formula? Include 1, 2. Okay, double the time. So 2 IM by pi. Okay. So IM by pi into what happened? Resistor RL is equal to. So what is your IM? Two resistance involved, right? The same. The second question I think so we discussed. Okay, the same thing here repeated, the same formula. So we having a two resistors connected in a, this is forward resistance and load resistance connected in a series. Series means you should add two resistance value. So Vm instead of I, what is your Ohm's law? I is equal to V by R, right? So since Im is equal to Vm divided by Rf plus RL, Vm is equal to, so this is your value, just substitute your Rf and RL, two resistance value 25 plus 800. Okay, so you just substitute the values. So Vm, the value of, sorry, VDC is given. VDC is 50 voltage given the question and Vm value is Vm you are supposed to calculate. Calculate AC voltage is given no in the calculation part. Question asked is Vm. So what is your Vm? Take it in the left hand side. Remaining you substitute. Substitution. After substitution, you are getting a value of 162 voltage. So total AC voltage required for this question is 162. Okay. So the next question is a full wave rectifier. You solve this question. Don't see the answer, you solve this question. Without seeing the answers, solutions, you try in your notebook. Just only the formulas you require. While preparing gate preparation, definitely you should maintain a separate note for each and every subject and you just practice it. Before practicing, you should memorize all the formulas in one page. You just write all the formulas. It will be useful for your for preparation. During preparation time, it will be helpful for you while writing when you write this formulas in your notebooks. Okay, be thorough with your formulas. Whether it is full wave or a half wave. First, you wrote the questions. Yeah, full wave rectifiers uses two diodes. Internal resistance of each diode. The internal resistance that is called as an RF. Okay, RF is nothing but an internal resistance of each and every diode. Full wave rectifier means how many diodes? Two diodes. So all the formulas and all the values will have a two value. Okay, twice the value of half wave. So while writing the formulas, be careful in that part. Twice the value. Okay. The internal resistance of each diode may be assumed as constant at 20 ohms. So RF value is what? 20 ohms. The transformer RMS secondary voltage from center tap to each end of the secondary is 50 voltage and load resistance is 980 ohms. What happened? Another resistance value RL. Okay, what is that 50? What is that 50 voltage? The transformer. Okay, here in the full wave rectifier they are using center trap transformer. Center trap transformer secondary winding. From the secondary winding output we are getting 50 voltage. So that is the value of 50 voltage. Okay, so what is the question asked? Find the mean load voltage. Second part is RMS value of load current. So two parts given, two question asked, mean load current and RMS value of load current. So first you write the given data. What are the given data? Both resistance value given, RF 20 volts and RL 980 volts. Okay. So first you calculate what is your AC voltage. First you calculate VM and then IM. What is VM? What is your VM? VM is nothing but root 2 into secondary voltage, right? 50 voltage is given in the question. So what happened? 50 into root 2 is equal to 70.7 voltage. Okay, next one is what? Maximum load current. In maximum load current, IM. I formula Ohm's law, V by R. Both the resistors are connected in series. So one is diode resistance, internal resistance 20 voltage is given. Another one is a load resistance, that is RL value is 980 ohms. So both are connected in series, so both you add it. So 70.7 voltage divided by additive value of two resistance is equal to 70.7 milliamps. Okay. Don't do mistakes in milliamps, microamps. Okay. If you are doing mistakes in that part, means the total value will be changed. So the total answer, that is the final answer, it will be wrong. So be careful in that part. So mean load current. What happened to your mean load current? You know the formula, no? IDC is equal to 2IM by 5. So in 2IM, IM value is already calculated. So 2 into 70.7 divided by 5. So what happened? 45 milliamps. The next is RMS value of load current. What is your RMS value? IRMS. IRMS is what? IM by root 2, no? IM by root 2. What is your IM? What is IM? IM is your load, maximum load current. VM is maximum load voltage. So IM by root 2. What is the value of IM you got? 70.7 divided by root 2. Okay. So the value is 50 milliamps. So for this question, for the first option, first equation, the mean load voltage, the mean load current. So for the mean load current, IDC is 45 milliamps and RMS value of load current is 50 milliamps. Okay. We are moving on to the next question. Next question is this. You solve this. Next question is a power supply A delivers 10 voltage DC with a ripple of 0.5 VRMS, while the power supply B delivers 25 voltage DC with a ripple of 1 millivolt RMS value. What is better power supply? Solve this question fast. What is your answer? What is the better power supply? For a supply A, the lower ripple factor of a power supply, which one is a better one? You analyze both. For a power supply A, the ripple factor. What is your ripple factor formula? Ripple factor is equal to, you should very strong with your formulas, okay? VAC divided by VDC. What is your VAC? What is your VAC? VAC value is what? Ripple factor, ripple of 0.7 VRMS, right? So that is 0.5. Okay, for VDC, it is 10. Okay, it is 10 for VDC. For supply 1 this is what for supply 1, that is A. Power supply A delivers 10 voltage. Here it's given for supply A, what is the value? 10 voltage and 0.7 for B, 25, okay? 0.5 and VDC value is 10. So calculating in terms of percentage, what happened? 5%. Okay. Next for supply, the same method, same step, same formula. Apply for a B1. Just you are going to compare both the values. That is both power supply A and power supply B, and finally you are going to compare which is for a better power supply. Triple factor VAC again. What happened to your supply 2? Power supply B. Power supply B delivers how much voltage? 25 voltage. Okay, DC with a ripple of 1 millivolt RMS value. So point, that is 1 millivolt converter. Or you just put 10 into 10 power minus 3. Okay, don't do mistakes in this part. Be careful when you are leaving this part, means you are just substituting one, means the whole value will be wrong. And then finally when comparing these two values, definitely you will do mistake. Wrongly you will compare. That's why I'm telling, while writing this m value, that is milli or micro or nano, whatever it may be, so be careful in that area. Okay, so 0.001, or you can also write 1 into 10 power minus 3, okay, divided by 25 into 100, that is 0.004 percentage. So which one is a better one? Clearly the power supply B is better. Okay, clear. So here we are stopping this concept, that is class today. Now here we'll discuss the next topic in the next class. Okay, ma? Thank you very much, ma. Thank you.